So we have a lovely test here. Calculus 2. All right, so this is locally known as Math 1660, and it's the third exam. Now, in Calculus 2, the third exam means we're talking sequences, and we're talking series, and we're talking Taylor stuff. So there's going to be a lot of good things for us to get to. We have 10 problems, 6 multiple choice, 4 workout, so we're going to have a good time. But of course, before we do anything, always remember, write down your name and write it legibly. Because if we don't put our name, we won't get the credit for all the good stuff we're about to do. Let's begin. Number 1. Define the sequence a sub n recursively by a sub 1 is 4, and for n bigger than 1, a sub n plus 1 is 2 over 1 plus a sub n. And we have a couple of choices here. Now, a couple of them seem kind of outrageous. Negative numbers? Because what do you see? We start with positive, and you say, look, if you start with a positive, you plug it in, you're going to get a positive back. So you always are going to keep getting positives back. So you shouldn't end up with any negatives. So even if we did nothing else, we could say, look, it's definitely not going to be those two. But we can do something else. We have that our a sub n is convergent. What's the limit L? Well, we say, what's going on? That says a n plus 1 is 2 over 1 plus a sub n, which for large n, this is getting close to L. And that's 2 over 1 plus, and that is getting close to L. The punchline is it's convergent, so at the end, way down there, so far down, like, wow, look at you, you're so far away. That's converging. So whatever the answer is, it has to satisfy L times 1 plus L equals 2. And we can actually just sit down and now figure out which one of these actually does that. Well, 0 times 1, no. 1 times 2 equals 2, yes. And 2 times 3 doesn't equal 2. So the answer is going to be 1. Now, even if you don't see that, you could say, well, that's L squared plus L minus 2 equals 0, right? Distribute, bring the 2 across. Then that factors into L minus 1, L plus 2, right? L squared, 2L minus L minus 2 equals, yep, it all works out. And that leaves you with 1 or negative 2. And that comes back to our previous discussion. Negative 2, hopeless, right? You can't start with a positive and get to a negative. So there's no way you would ever get to negative 2. All right, so that's number 1. Number 2, apply the ratio test to the series. That series right there. Now, even if they hadn't told us to apply the ratio test, we would say, you know what? We see some factorial terms. When we see factorial terms, we think ratio test. And so we would have probably gone there on our own. And find the limit as n goes to infinity, an plus 1 over an. That's the ratio test. Now you might say, well, wait, what is a sub n? Well, a sub n is this piece right here. So this is our a sub n. So notice absolute values here, but there's no negative signs, so we don't have to worry about the negative part. All right, so what do we have? Limit as n goes to infinity, an plus 1 over an. Well, to find an plus 1, what do? Everywhere where you see an n, put an n plus 1. And here, I strongly recommend use parentheses. They are your friends. 5 to the n plus 1. Oh, limit as n goes to infinity. I should write that down. Technically, since, this is multiple choice, we don't have to be too careful with our notation, but we should still follow good practices. 3 and then 2 times n plus 1 and factorial. All right, divide by an, which is the same as multiplying by the reciprocal. So we're going to have a 3, a 2n factorial, an n factorial squared, and a 5 to the n. Well, the 3's are gone. Ah, pow, pow. And you don't have to make sound effects when you're doing that, but it feels good. And what do you do? Well, we can also see, look, you have 5 to the n plus 1, 5 to the n. Well, 5 to the n plus 1 is really 5 to the n times 5, and then you can cancel 5 to the n's. So we're like, wow, we're doing great. Now, what do we have here? Well, okay, so we have a5. Might as well pull that out. Don't forget it's there. And then everything else is a factorial. Now, what we can do is we can say we want the factorials upstairs to help us cancel with the factorials downstairs. So how do we do that? Well, for example, this n plus 1 factorial, I can pull off the first term. So another way to write this n plus 1 factorial is as n plus 1 times n factorial squared, right? Pull off the first term, everything else is still a factorial. We still have a 2n factorial upstairs. Downstairs, well, we have an n factorial squared. Now, note, that's 2n plus 2. So what do? We start pulling things off. And we say, okay, so that's 2n plus 2. Well, that's not quite to 2n yet. Next term would be 2n plus 1. Getting closer. The next term would be 2n. We're like, great. Then just do the rest of it as a factorial. So pulling off 2 terms here instead of just the 1. Well, at this point, we're like, nice. Because what happens with our factorials, those really pesky terms that are just gigantic? Well, those cancel, and those cancel. And now you say, oh, well, gosh, this is looking great. Because what do you really have? Upstairs, well, we have an n plus 1 times an n plus 1. Now downstairs, we have 2n plus 2, which is really 2 times n plus 1, and 2n plus 1. You can cancel off an n plus 1, and then you say, well, wait, that I can figure out. What's happening to n plus 1 over 2n plus 1? This is going to go to a half, leading coefficients. Don't forget that term. So what do you have? We have 5 times a half, or 5 fourths. There we go. And that's the answer. All right, good. So when you're dealing with factorials, and they like to throw in a factorial once or twice on one of these exams, remember, you're going to do that ratio test and just pull off enough terms so you can get the cancellation that you need. All right, moving on to number 3. The third term in a Taylor polynomial generated by the function f of x equals p 1 plus 2x to the 5 halves and centered at a equals 0 is 30x squared. So it's being very explicit by what it means by the third term. 30x squared. The question, find the value of the constant p. So where do we begin? Well, this is testing us on a couple of things, but the main thing is saying, do you understand what Taylor polynomials look like? And the answer is Taylor polynomials are storing information about derivatives. And so, in particular, what does it look like? Since we're centered at 0, we'd look like the following. We'd look like f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and we keep going all the way up to someplace answered at 0 over n factorial x to the n. We stop. So that's what a Taylor polynomial is doing. It doesn't tell us the degree, but we don't need to know the degree because we're told that, oh, this piece right here, that is 30x squared. So we're like, oh. So that tells us if we take f double prime as 0, divide by 2 factorial, we get 30. Okay, another way to say this is that f double prime of 0 has to equal 2 factorial is 2. That has to equal 60. So by knowing we have something in the Taylor polynomial, now we know something about the second derivative at 0. And we say, okay, so that's going to come into play. In fact, that's the only thing we have. So it better come into play. So we say, well, let's look at what we have here. We have our f of x. So let's take a look. F of x is p 1 plus 2x to the 5 halves. We need to get to f double prime, so we start with a first derivative. So the 5 halves comes down. There's 1 plus 2x to the power 3 halves times 2 by the chain rule. So notice here the 2's cancel. Do it again. F double prime of x. So we have the p, the 5. Now the 3 halves comes down. 1 plus 2x to the power of 1 half. Chain rule again, times 2. The 2's cancel. And from here we can plug in. We're going to say, well, what happens to f double prime of 0? We get p times 5 times 3. That's 15p times 1 to the 1 half. So that's 15p. And now we're like, ooh, we're there, right? We see it. What do we see? We see two expressions for f double prime of 0. So we come to the conclusion that 60 must be equal to 15 times p, or that p must equal 4. There we go. Woohoo! So this is good. It's testing us on Taylor polynomials. I like this problem. I'm not the one who wrote it, but I like it. I like it. And I think, Taylor polynomials, they get a bad rap. They're beautiful, wonderful ideas. It's just saying, hey, we're going to do our best to imitate the function by a polynomial. And we love polynomials. They're super easy to work with. All right, let's keep going. To number 4. For determining the convergence of the series, the sum 3 to infinity, n squared plus n3 plus n to the 4th over 1 plus n cubed plus n to the 6th, we'll use the limit comparison test. In fact, it's a very good thing to use the limit comparison test on something crazy like this. With another series, so that the limit as n goes to infinity of a over bn is something L, 0 less than L less than infinity, which of the following series will work for the test? Okay. Now, what's the limit comparison test? Here's how I like to think about the limit comparison test. It says, get rid of the noise. Okay, what do I mean by that? Well, when we're trying to understand convergence or divergence, we're looking at what happens way down there, like way down there. What's happening at the tail? It's not the first couple of terms that tell you if it converges. It's how quickly it's going to 0 down at the end. So what do we want? Well, we want to understand, hey, what's this really behaving like? And in particular, what can we ignore? What's driving the decay? So here's the basic strategy. When we see a limit comparison test, we say, okay, keep the big terms. And you do it for both upstairs and downstairs. All right? So that's the idea. Those are telling you how fast things are growing. And now, if we understand that, then we can say, hey, it simplifies. So essentially, we're going to get rid of all the plus signs. That's our goal. We want no plus signs. So, with that in mind, we say look at n squared plus n cubed, n to the fourth. 1 plus n cubed plus n to the sixth. Upstairs, what is the largest term between n squared, n cubed, n to the fourth? The answer, n to the fourth. Higher exponent, bigger value. Downstairs, we have 1, n cubed, n to the sixth. What's the biggest term? N to the sixth. And now we say, oh, so what's going to happen is the limit comparison test says just keep the highest growing terms, and that's going to be what it behaves like. So this is approximately like n to the fourth over n to the sixth, or if you simplify, 1 over n squared. So this is what we compare it to. So we're getting rid of the noise, right? Get rid of the noise, get rid of the funk. Get all the lower order terms out. Focus on the highest terms, and that will help us figure out what's going on. So that's what we want to compare to. So now we look for 1 over n squared, and you see it right there. So our answer is C. That's the idea. Now I like this one, but I'm definitely biased because I can tell I wrote this one. That feels like me. That feels like me. All right, on to number 5. And I'll go ahead and say it. You're probably already suspecting it. I wrote this one too because there's an arctangent. Ah! Now, it's not true that every problem with an arctangent is one that I wrote, but it is true I like to write a lot of problems that involve arctangent. So, all right. Well, what's going on? We're asked which of the following series diverge. Okay, so let's be careful here. Notice how they made it bold and italicized. So we want to find those series which are not converging. So we say, okay, well, with that in mind, what's going on? Let's start with 1. Here, the nice thing we see about 1 is there's this minus 1 to the n. When you have a minus 1 to the n, you're alternating plus, minus, plus, minus. So then convergence can become a really quick question. What's happening to the other piece of it? So there's an alternating piece, there's a size piece. And now we say, well, what's happening to 1 over arctangent of n? Well, that has the question, what's happening to arctangent? And if you know arctangent, who doesn't know arctangent, then you know that arctangent has this behavior. For large values, it's approaching an asymptote of pi halves. So this is approaching the number 1 over pi halves, or 2 over pi. Now, you might say, okay, but what do we know about 2 over pi? Well, one thing we definitely know is it's not going to 0. So it's alternating, cool. It's even decreasing, cool, but it's not decreasing to 0. So what's going to happen? This will have to diverge. All right, so we know that our answer has to include 1. So that knocks out B and D because they don't include 1. So we say, okay, well, that leaves us with a couple of possibilities. Okay, well, we have to check. Let's see, can we check? Well, let's check 3. What's 3 going to be? Now, 3, we can kind of eyeball and say it's going to converge because what do you see upstairs? Polynomial. What do you see downstairs? Exponential. And one of the things you want to learn is relative sizes of things. Polynomials, yes, they grow, but exponentials leave them in the dust. So the exponential is dominating, and 1 over 2 to the n, that's convergent. So essentially the idea is by sizing it out, we say, okay, this should converge. We can make it more formal, say, well, let's do a root test. And so take things to the 1 over n power. And if you do that, what's going to happen? Well, that's n to the 1 over n squared. Downstairs it's 2. And n to the 1 over n goes to 1. So it goes to a half, which is less than 1. So the moral, by the root test, this converges. Okay, so that says what? Well, we can't include 3, right? So anything with a 3 is out. So that rules out E. Okay, so that means we're down to either A or C. Ooh, okay. All right. So we've got to figure out this one. Number 2. Now, number 2 is an interesting sum. It's kind of a classic sum because it's essentially the sum that one very particular tool gets used on. And this is the integral test. Okay, so what's going to happen here? Well, you're going to do the integral from 8 to infinity of 1 over x square root log x. Now, here's the issue. 1 over n diverges. It's a harmonic series. 1 over n squared log n, well, it's a little bit below the harmonic. And so the question is it just enough below or is it also divergent? That 1 over n, that's a famous, or perhaps we should better say, infamous series. Now, what can you do? Well, here you do a substitution. U equals log x. Du is 1 over x dx. And we say, aha, this becomes integral log 8 to infinity, right? Plug in the 8, plug in the infinity, of course, whatever plug in infinity means. Well, okay, what happens as you let the input get large? And what do we have? Well, you get u minus 1/2 du. And this, if you integrate, right? Why minus 1/2? Well, because there's a square root of u downstairs. And square root is a half, downstairs minus. Add 1, you get to the power, that's a half, and multiply it by the reciprocal, so it's 2 square root of u. Evaluate from log 8 to infinity. And, well, hopeless. It's blowing up. This diverges. And you say, well, wait, that just says that the integral diverges. But yes, because it's tied by the integral test to whether the sum converges. So that says we need to include 2. So 2 is in. So A is out because it doesn't include 2. The answer is C. 1 and 2 diverge, and 3 doesn't. Okay, whew, that was a good one. All right, now that brings us to our last multiple choice problem. Number 6. Find the sum of the following convergent series. And we say, well, that's an interesting series. What do you have? It's the sum n equals 2 to infinity, negative 1 times to the power n plus 1 times 5 to the negative n. Well, what can we do? Well, one thing we can do is we can think about what this looks like. Spoiler alert, it's geometric. And so we can say, well, hey, this inside piece is the same as minus 1 to the 1 times minus 1 to the n, and downstairs is 5 to the n. Or we can say, hey, this looks like minus 1/5 to the n power. So that's really what we're summing. So this is the sum, n equals 2 to infinity. And let me go ahead and put the minus outside. Minus 1/5 to the n. Okay, now we're ready. How do you sum a geometric series? Because this is geometric, because you see something to the end. There's not a lot of things that you can find the value of that are convergent. There's really a short list of 3 things. And the biggest one is geometric. There's other things that are telescoping. And if you get really lucky and happen to have something which is a Taylor series, but again, we're geometric. So here's the rule. So if you're summing a geometric, so the sum of something geometric, you do the following. It's the first term in your series over 1 minus r. Now, for us, what's the first term? So the minus is out there in the front. What's the first term? Be careful here. It's n equals 2. So the first term is minus 1/5 squared. Divide by 1 minus r, which is minus 1/5. Okay, so that is the answer. Well, that's not any of the options, because those crazy people, they said, let's simplify. Typical math nerds, always trying to simplify things. All right, so there's a minus sign. 1/5 squared, or negative 1/5 squared, will become 1 over 25. Then we're going to divide it by 1 minus a fifth. That's 1 plus 1/5. Now notice 1 is 5/5. 5/5 plus 1/5 is 6/5. Well, multiply by the reciprocal. Minus 1 over 25 times 5 over 6. You can cancel off one of the 5's. You get negative 1 over 5, 1 over 6, which gives us negative 1 over 30. Aha! The answer was B, minus 1 over 30. And yes, you can get negative. It's not too surprising, given that our first term is negative. All right, well, with that, we're done with the multiple choice. It took us a minute. It took us more than a minute, but that's okay. Now we get to go and do the workout ones. And so we got to be a little bit more careful here. Show our work. Follow the directions carefully, because we want to get all the points. So let's begin with number 7. Find the interval of convergence for the power series below. State any convergence test you use. Classic problem. So this is one you almost always know is coming. So be ready for it. Now, when we're doing interval of convergence, don't worry about this part. That you can ignore. The question is the tail. What's happening way down there at infinity? That's going to help you know converge or not. And we're always going to start the same way. So we're going to look at it and say, this is our typical a sub n. And so the first step is we're going to find the radius. And how do you find the radius? Well, you can either do a root test or a ratio test. And here's the very simple thing. If you see a factorial, it's a ratio test. If you don't see a factorial, I always suggest a root test. 95% of the time, the root test is the easier test to apply. Is 95% 100%? No, it is not. I do know how math works, but it's high enough that that's where we're going to go. Okay, so that's our direction. We're going for a ratio test. Sorry, a root test. I remember what I just said. So how does the root test work? We're going to take a limit as n goes to infinity of absolute value a sub n to the 1 over n. Now, when we take that absolute value, well, that negative 1 to the n is just completely gone. Because the only thing that negative 1 to the n is doing is plus minus, so that's out of there. So this becomes the limit as n goes to infinity. Upstairs, it'll be absolute value of x minus 4 to the n, and downstairs it'll be 7n times n, all to the 1 over n power. And if we break it down, or really I should say distribute the 1 over n power into each term, upstairs to the n to the 1 over n, well, that just leaves us with an x minus 4. Downstairs, 7 to the n to the 1 over n is a 7, and then you have n to the 1 over n. And we say, well, the only place this shows up is down here, and we know that limit. That limit is so classic, it's actually on the formula sheet. That goes to 1. Okay, so this becomes x minus 4 over 7. And now we pull out, what does the ratio, root test. I can say root. You know, one of the hard things is they both start with an R, and once you start the R sound, you almost have no time to recover. What does the root test say? It says, and I'm going to go ahead and just point it out. It's over here. This is the root test and the ratio test. If your limit is less than 1, it converges. So you say, okay, cool, we want this to be less than 1. And now we make a note. So by root test, ratio test, I think I'm just going to do this for this whole problem, aren't I? I'm going to keep saying the word root and then correct myself. I am so sorry. I'm so sorry. I'll do my best not to make that mistake too many more times. By the ratio test, and why do we say it? It says state any convergence test you use. That's the convergence test we're using, so we got to say it. We know converges for absolute value of x minus 4 over 7 less than 1, or absolute value of x minus 4 less than 7. We also know it diverges by the same test, the ratio test, for absolute value of x minus 4 bigger than 7. So essentially, what happens is the first step gives you almost everything. Almost everything. What doesn't it give us? Well, it leaves us with 2 points. So that's where we have to go into our second step. So our first step, it finds the radius, and at this point, so after step 1, I just want to point out where we are. What can we say? Well, our center is at 4, right? Because it's x minus 4. So we are centered at 4. We go out 7 in each direction. That'll get us to 11 and negative 3. So, right, 4 plus 7, 4 minus 7. We are good to go in between. We know we are not going to converge out there. So that leaves us with the endpoints. So that's our second step. Step 2. So here we go. Step 2, our second step. Check the endpoints. And in some sense, the endpoints, you cannot use the root test or the ratio test. Both of them will fail at the endpoints by design. So we say, okay, what happens at x equals negative 3? Well, we get the sum, n equals 1 to infinity, minus 1 to the n, minus 3 minus 4 to the n, over 7 to the n times n. Minus 3 minus 4 is negative 7. So we have a negative 1 to the n, a negative 7 to the n, and a 7 to the n. What does all that become? Well, if we maybe do one more thing here, we could say, look, this is there's a 1 over n here, and then we have a -1, a -7, and a 7. All of that goes to 1. So really, we're looking at sum n equals 1 to infinity of 1 over n. So what do we know about this sum? Famous sum. Diverges. Why does it diverges? Why does it diverge? It diverges because it's a harmonic sum. It's that one sum right at the very edge. So that's our test, right? Say, look, we know what the sum looks like. Oftentimes, on a side note, you'll get sort of two things you're kind of looking for. You might have one of your two is alternating, then use alternating series test. Spoiler alert, we haven't done both sides. And the other thing you might see is p-series. This is also a p-series. You can say, oh, it diverges by the p-series test. Okay, so what does that tell us? Well, it tells us we don't include -3. So -3 is out of the interval. But that still leaves us with a second point. So we say, okay, let's check that point. At x equals 11, well, we get the sum, n equals 1 to infinity, -1 to the n, and then it's 11 minus 4 to the n over 7 to the n times n. But 11 minus 4 is 7, so it's 7 to the n, which cancels. So we get a sum, 1 to infinity, of -1 to the n over n. What's going on here? It converges. Well, what's the difference? You have that extra plus minus. And so you say, by alternating series test. Well, we're alternating. We have that plus and minus, and the terms decreasing down to 0. So you do include the endpoint at 11. All right, so now we're done. We have all the information, but our last thing to do is to combine. So combine the information from our first step and our second step. We have that our interval is -3, strictly less than x, less than or equal to 11. Or, of course, you can do other notation, -3, 11, and do a parenthesis on one end, square bracket on the other end, whatever notation you're comfortable with. And that's the process. And it's always the same when we're talking about interval convergence. Find the radius, root test or ratio test. Find what happens at those two last endpoints. Put it all together. It's a process, but it's a predictable one, and it's one that you can do. All right, let's move on to the next problem. Woo-hoo! All right, number 8. Consider the following series. Okay, I have considered it. Well, what is it? The sum, 3 to infinity, 4 over k plus 2. And part A, find an expression for Sn, the nth partial sum of the series. All right, so what's going on? We start at 3, we go to n. Now, we're also looking at part B, where it says find the overall sum of the series, and you notice, you're like, oh, because there's only a couple things where you can actually find the sum of a series. Geometric is the big one. This is not geometric. Why is it not geometric? Because this k is not in an exponent. Geometric, that's where it would be. So, okay, it's not geometric, so that leaves us with telescoping or Taylor. It doesn't look like Taylor. So we're like, okay, we're thinking telescoping. So what we need to do is rewrite it in such a way that we get cancellation. So we're going to channel our inner partial fractions. And we say, let's practice our partial fractions. And you're like, I thought we were done with partial fractions. But it's one of those things, just when you think that you're out, partial fractions pulls you back in. So Here we go. We have 4 over k times k plus 2. And we're going to think of this, and we're like k is our unknown. So a over k plus b over k plus 2. Clear the denominator. So multiplying everything by k times k plus 2. So 4 is equal to a times k plus 2 plus b times k. Now, make good choices, such as watching videos to prepare for the exam. Great choice. Thanks for being here. I'm glad you're with me. And also, choosing things like k equals 0. What happens when we choose k equals 0? Well, this term gets knocked out. So we get that 4 is equal to 2a, or a equals 2. When we plug in negative 2, that will knock out the k plus 2. So we'll get 4 equals minus 2b. Or wait, or is it 2b? No, it's minus 2b. Okay, or b is minus 2. And so we say, oh, so this is really 2 over k minus 2 over k plus 2. Now here's the idea. Notice that these are very similar, but one is positive and one is negative. That's good, because the idea of telescoping is you get cancellation. So for every plus 1, you want a minus 1. One other thing to note. Look at the offset. Here we see k. Here we see k plus 2. How far apart are these two terms? They're 2 apart, right? Plus 2. Now what that's telling us is that when we get cancellation, we're not going to look, if this is our first block, we don't look in that block, we look in the one after it, right? We look 2 away to get our cancellation. So, more particularly, let's look at our Sn. We'll start our Sn, that's our sum from 3 to capital N of 4 over k times k plus 2. Well, that's our sum from k equals 3 to capital N of 2 over k minus 2 over k plus 2. And now we're going to write some pieces down. So we'll start with 3. So that's 2/3 minus 2/5, right? K plus 2. Plus 2 over 4 minus 2 over 6. Plus 2 over 5 minus 2 over 7. Plus, I'll do one more to help us see what's going on. 2 over 6 minus 2 over 8. Plus, dot, dot, dot. Now, I'm going to start at n minus 2. At n minus 2, we'll have 2 over n minus 2 minus 2 over n. Then I'm going to do n minus 1, 2 over n minus 1, minus 2 over n plus 1. Oh, and then I didn't give myself quite enough room, and then at n, it's 2 over n minus 2 over n plus 2. And why did I start at n minus 2 on the end? Just to sort of capture that pattern of cancellation going on at the end as well. So, what's going to happen? We should see lots of terms canceling. The minus 2/5 go 2 blocks over. There should be a plus 2/5. They cancel. This 2/4 go 2 blocks over. Oh, wait, not the 2/4, the 2/6. Sorry about that. The 2/6 will cancel. The 2/4 won't cancel. The 2/7 would cancel with something inside. 2/8 would similarly cancel with something inside. Now, at the other end, do you see this 2 over n? You go 2 blocks back, and that cancels. Similar, this 2 over n minus 1, 2 blocks back would cancel. This 2 blocks back would cancel. So, what's left? Well, because your offset is 2, you'll have 2 terms at the start, 2 terms at the end. And in particular, we get the following. This is equal to two terms at the start that don't cancel, 2 over 3 plus 2 over 4, minus the two terms at the end that don't cancel, 2 over n plus 1 and 2 over n plus 2. And that's our S sub n. Okay, good. So, what's the idea? If we do have a telescoping series, write out enough terms to get the cancellation pattern going. You'll get some terms left at the start, you'll get some terms left at the end. And as I said, the offset should tell you how many terms you have at the start and at the end. So offset of 2, 2 from the start, 2 from the end. Now, part B, find the overall sum of the series. And the idea is, well, the sum of the series is going to be, take the limit as capital N goes to infinity of Sn. So that's the limit as capital N goes to infinity of 2 over 3 plus 2 over 4 minus 2 over n plus 1 minus 2 over n plus 2. And then you're like, hey, the parts at the end poof, disappear. So that's the idea. Now, double check. Sometimes they don't. We've put before examples where the parts at the end don't disappear, so that's why it's important to check. This is being a very rigorous. And we say, oh, well, we get 2/3 plus 2/4. We can get a common denominator of 12. That would be 8 over 12 and 6 over 12. 12. I know what 12s look like. And so 8, yes, just double checking here, times that by 4 over 4, 3 over 3. That makes it 14 over 12, or we can divide by 2, 7 over 6. I probably should have noticed that 2/4 is a half. I could have made that simplification earlier. Ugh. All right, well, but we got there in the end. So it sums up to 7/6. And there you go. There you go. All right. Well, good. We're doing all right on time, but we still have 2 problems left. So let's focus. 9, part A. Use known Taylor series to find the Taylor series centered at a equals 0 for f of x equals 9x e to the 3x. So notice what it's saying, not what it's saying, not telling us to do. It says, hey, don't find the Taylor series. It says, build off of stuff you know. So we're like, oh, cool. So let's look at our arsenal of Taylor series. We have a whole bunch written into our formula sheet. And we say, okay, we've got cosine, sine, 1 over 1 minus z, 1 plus e to the alpha, and e to the z. And we look at this and say, does this look like any of those? And we're like, oh, e to the z. Nice. So we're going to build off of that one. All right, so what do we have? Well, let me write it in the way, well, I'll write it as it's written in the formula sheet. So it's e to the z is the sum, n equals 0 to infinity, z to the n over n factorial. However, when I'm thinking about it, I say, look, I'm going to think of z as just being a box. So I have e to the box. That's going to be the sum, n equals 0 to infinity, box to the n over n factorial. And now the question, what's in the box? What's in the box? What's in the box? Right? If we can figure out what's in the box, then we can make this work. All right, now, one other philosophical pause here. When we're after a Taylor series, it's the same as thinking it as though we're after an infinite polynomial. Now you might say, well, what do you mean by that, Steve? Well, what I mean is think polynomially. And notice 9 times x. That x, that's kind of polynomial flavoring. So we're okay with that 9x being 9x because we love polynomial pieces. So it's really like, hey, we're going to make that e to 3x look like polynomial. That's what we're building up to. And then we'll just multiply the 9x through so that we have our big infinite polynomial. Oh, yeah. All right, so let's work here. F of x is 9x e to the 3x. Do you see the box? Haha. What's going into the e? It is the 3x. Okay, so we're like, well, this becomes 9x, the sum, n equals 0 to infinity of 3x, right? That's our box. Here's our box. So it's 3x. And I'm going to be very careful here, to the n over n factorial. So it's everything inside the box gets raised to the n. Not just the x, the 3 inclusive there. Now we're like, this is good. We're going to do a little bit more here. Whoops, let me switch colors. I don't want to overuse my red. So we're going to put that 9x, going to move it in. And so if we do that, well, what do we have? We have a sum, n equals 0 to infinity, 9, and because I see there's a 3 there, I'm going to take advantage of the fact that 9 is very 3-ish. So I'm going to make that 9 a 3 squared x. Then we have a 3 to the n, x to the n, and then an n factorial. So there's the 9x. And now I distribute the nth into both terms. Or I can say this is the sum. N equals 0 to infinity. All right, this says 3 to the power n plus 2, x to the power n plus 1. Divide that by n factorial. And there we go. That is our Taylor series. Now, we could have done other things to it. We could have done some index shifting, but we don't need to do that. That's a beautiful, beautiful answer. All right, part B. Now, notice part B is different from part A. So it says, let g of x be a function, right? This is f of x, this is g of x, different thing. G of x is this sum, n equals 3 to infinity, x to the power 2n minus 1 over n factorial. Use Taylor's formula to find the 11th derivative at 0. They might say, what? What do we mean by Taylor's formula? Well, Taylor's formula says that g of x looks like the sum, n equals 0 to infinity, of the nth derivative at 0 over n factorial x to the n. Okay, so let's start by looking at this part. When will I see the 11th derivative? Well, that will be when n equals 11. So we're like, okay, in particular, this looks like dot, 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 plus the 11th derivative at 0 over 11 factorial x to the 11th plus dot, dot, dot. And you're like, okay, that's cool. So how do we use that with this information? And here's the thing. We have two series, two infinite polynomials. When are two infinite polynomials equal to each other? When all their coefficients match. So we say, so I want to say what's going on with x to the 11th there. Well, so let's look at x to the 11th. So we have our sum, n equals 3 to infinity, x to the 2n minus 1 over n factorial. What is that? Well, that equals ... Now, be careful here. We want to have x to the 11. Which choice for n gives you x to the 11? Look at the exponents, 2n minus 1. So what do you choose for n to get to 11? So you're going to get x to the 11 over 6 factorial plus ... Right? So I'm plugging in n equals 6. And now we say, ooh, we're there. Because now we can compare these two big polynomials, and we say, now that we see the x to the 11th terms, we have to have what's in front of them matching up. So our final thing is set the pieces in front equal to each other. So we're going to take g, 11th derivative at 0, over 11 factorial has to equal 1 over 6 factorial. Or we get that the 11th derivative at 0, multiplying across, is 11 factorial over 6 factorial. And there we go. That's the idea. It's that's a beautiful idea. Cool, but let's not dwell on it too long. Good problem. I didn't write this problem. You know what? I got to pause for a second. There's a lot of good problems on this test. I actually like this one. And let's hope that the last one is good too. And I'm going to tell you already, I'm going to be a little bit biased. I'm going to admit it up front. I wrote this one. A lot of words here. Okay, but that's all right. That's all right. This question deals, all right, number 10. We should have said that. 10. Whoa. This question deals with the converging alternating series. Okay, so we're told already it converges. That's cool. We could have told them if they wanted us to, but all right. So the alternating series test conditions for a series to converge. The alternating series test gives conditions for a series to converge. You know, when it's late on a test, sometimes it's easy to miss some words. One condition is that terms in the series alternate signs, going between plus and minus. Hence the name alternating series. That's this minus 1 to the n. What else needs to hold? Now, this is a generic question. It's asking the question that says, hey, do you understand what the alternating series test is? So, okay, so the alternating series test gives technically 3 things that needs to be true. It needs to alternate. What else do we need? We need to have that the rest of the terms shrink in size, but they also need to shrink to 0. It's not enough to just get smaller. It has to go to 0. So what else needs to hold? The terms in absolute value decrease to 0. Now, there's a lot of ways to say that, and essentially, there's 2 important things that you need to bring up. You're going down, and you're going to 0. So as long as you capture both those flavors, you would have gotten full points on this one. All right, so that's part A. Now, part B. And this one is Fantastic Four. The Fantastic 4 points. Determine if the series we are considering converges absolutely or converges conditionally. State any convergence test you use. So this is absolute versus conditional convergence. We know it's one of those because we already know it converges. So how do you test? Well, what you do is you say, okay, consider the following sum. You drop the alternating part. So that's going to be the sum from 6 to infinity of 1 over square root of n. So the question is, do you need that plus minus? That's the conditional part of conditional convergence. Well, what do we have here? This is a p-series. So this is a p-series, and in particular, with p equals 1/2. Now, what do we know about a half? Well, true story, this is less than or equal to 1. So when p is small, that tells us it diverges by p-series test. So when when I say p-series, by the way, what is that referring to? A p-series, that's the sum n equals, well, in our case, 6 to infinity, 1 over n to the p. So you want p to be large. Large p is good. Anything bigger than 1, it converges. Anything less than or equal to 1, it diverges. So our conclusion is that our original series is what? Well, we know the original series converges, but drop the alternating part and then it diverges, so the original series converges conditionally. All right, so that's the fantastic 4 points in part B, which brings us to the final 4 points that we have to do. All right, the final 4 points. What is the smallest n for which the sum will be within at most 0.05, which is 1 over 20, of the total value of the series according to the error bound for alternating series? So one of the interesting ideas that we've been talking about in this course is to say, hey, we can approximate things, but how good is our approximation? An approximation is only as good as our error. And we talked about this, for example, when we talked about using numerical integration techniques. We can also talk about it in terms of series and saying, well, okay, I want to know the value of the series. I only need to know it to a few decimal places. How far do I have to add? So that's what we're essentially saying is, how far do I have to go out so I can guarantee that it's pretty close? Now, this is not saying what's the very first time you're within a certain error. It'll probably happen much sooner, but we just want to say we're guaranteed to work. And good news, if you know your formula sheet, right? Better know a formula sheet, then you can say, it's stored in there. And there's 2 places that you're storing information about essentially error estimates. And, well, there's actually more than that, but there's this one, and there's this one. So this is for the integral test. How far do you have to go? This one is alternating series test. And what's the clue that it's an alternating series test? You see there's an alternating series. What does it say? It says that if you have an alternating series, the distance between a partial sum where you stop versus the limit L, that's if you went all the way, is the next term. So we're jumping back and forth, but we're jumping smaller and smaller and smaller distances. So if we stop at any second, you can say, well, the worst case scenario is if you have to jump all the way. Okay, so that is the clue. Say, okay, so with that in mind, we say, okay, what's the smallest n? Well, what do we want? We want to say the following. So we want our L minus this sum, n equals 6 to capital N, minus 1 to the n, over square root of n. We want this to be small. Well, we want this to be less than or equal to 1 over 20. At most, 1 over 20. Now, here's the thing. This is what we want to bound by 1 over 20. So what we'll do is we'll sandwich in the next term. Now, this box is not the answer, but Well, what's the next term? The next term is ignore the plus minus part and think of n being replaced by n plus 1. So the next term will look like 1 over square root n plus 1. So now that's going to be what we get our answer from. So we start digging around. So, okay, let's start from here. We'll flip both sides. When you flip both sides, you flip the inequality. So instead of less than or equal to, it's greater than or equal to. Square both sides. N plus 1 needs to be greater than or equal to 400. Subtract 1 leaves you with n has to be greater than or equal to 399. So by the time we have added up to our 399th term, we're guaranteed that our error is at most the next term, which is 1 over 20. And we're done! Our final 4 points! We nailed it! Woohoo! Sometimes I don't enjoy the Calc 2 exams, but sometimes you get a good one. I think this was a good one. I already said that before. But I hope you enjoyed the next one too. Let's have good, fun exams. Thank you for joining me. I hope you learned something along the way, and I hope that this is helpful in getting you prepared and building up confidence. You can do this. Know your formulas, know how to use them, know the ideas. What's the big idea? The big idea? Polynomials are great, and let's make everything look polynomial. That's what we're going for. All right, well, good luck. I hope you do well. I hope I get to see you again. All right. Bye.